you up this time. Well, darling, just kiss me slow. Your heart is all I own, and in your eyes you're holding mine. Baby, I'm dancing in the dark with you between my arms, barefoot on the grass. We're listening to our favorite song. When you said you looked a mess, I whispered underneath my breath, but you heard it. Darling, you look perfect tonight.
Well, I found a man stronger than anyone I know. He shares my dreams. I hope that someday we'll share our home. I found love to carry more than just my secrets, to carry love, to carry children of our own. We are still kids, but we're so in love, fighting against all odds. I know we'll be alright this time. Darling, just hold my hand. Be your girl, you'll be my man. And I see my future in your eyes. Well, baby, I'm dancing in the dark with you between my arms, barefoot on the grass, while listening to our favorite song. When I saw you in that dress, looking so beautiful, I don't deserve this. Darling, you look perfect tonight. I have faith in what I see. Now I know I have met an angel in person, and she looks perfect.
I don't deserve this. You look perfect tonight. I found a love for me. Well, darling, just dive right in and follow my lead. Well, I found a girl, beautiful and sweet. Well, I never knew you were.
All right, it looks like it starts earlier. So, well, Well, there are some technical issues, but why don't we just start earlier? So I know a lot of you are probably staying up late last night just because you want to work on the project. But no matter what you have, I hope all of you can like the song we just played. Like at the end of today, before you submit your project, you can say, well, like the song, right? Perfect, like you, baby, you look perfect tonight, right? So hopefully you can say that to your project. So before we start, it's always a good idea to remind you where we are. And yes, in the last lecture, we talked about the Google file system. So today we are going to continue our discussion on Google file system, and we are going to talk about its competitor, how Microsoft is trying to implement its cloud storage. But before we start, it's always a good idea to see why we need Google file system in under the situation that we already have quite a few file systems for single machine. So the true answer is this, right? We know that data centers is becoming popular. However, if you think that the conventional file system can be a plug-in solution for the demand of data centers, that's completely incorrect because the workloads are completely different. So remember that we said that in the very early units, or say fast file system, what we have is that we think that most of the workloads are going to read large files. Well, sorry, are going to read large amount of files, and the reading is more intensive than writing. Then we have the log structure file system. The log structure file system is trying to tell us that the sequential writes is actually more important than that. Right. However, in data centers, it turns out that, well, because people care about the security of data, and data centers, they want to save money. So instead of using the best personal computer storage systems, so for example, like most of the data centers, they won't use solid state drives because it's too expensive. So the storage is based on very inexpensive disks, and that fails frequently. So if that's the case, then you have to have a file system that can tolerate that. And personal computers, although you have primarily reading streams, like the third one well, that's the assumption of fast file system. However, that's not true anymore because we have the big memory capacity. So, but when we go back to the data centers, because, well, the reason why we want data centers is because people believe they have big data, they want to process. So it becomes, again, they have primary reading streams of data. However, in comparison to the relatively small files for personal data, the data centers, they want large files. So that's also something that all previous file systems never tried to optimize for. However, for writing, it's similar to log structure file system. Again, that it's actually not similar to the goal of log structure file system, because for the log structure file system, we talk about we want to aggregate randomly accessed writes to be sequential writes. And because you have the logs everywhere in your system, so again, in data centers, you are seeing sequential writes because the workloads on the data center, in the data centers like key value store, they all have a log that try to aggregate all transactions into sequential writes. So it turns out that you again have sequential writes instead of random writes, and must support multiple concurrent operations. As thinking about that, you want a server to serve like thousands of clients. And the other thing is that they mentioned bandwidth is more critical than latency. However, in a personal computer, we care latency more. So those are different. And the data center workloads they have when designing the Google file system, one is the Google search, the other is the MapReduce and Bigtable as a key value store. And we are going to cover Google search next week, and we are going to talk about, well, probably not next week, next lecture. And we are going to cover a little bit about MapReduce today. And for Bigtable, it's a key value store. So I would leave it to, if you're taking a class like database, if the professor didn't teach that, ask him to teach that. And so based on those demands, this is what Google file system proposed. So first of all, programmers are lazy to change their behavior. So they still maintain the same interface in a way that the same open, close, read, write function codes, the same hierarchical directory structure of files. However, although it says we have hierarchical directory and files, but it actually uses a flat structure, meaning that the directory is just an illusion. And each file is decomposed into large chunks. So instead, in the past, if you remember what happened in UFS or log structure file system is that you have extents, and extents are different sized. And for Unix fast file system, each block is only about like 8 kilobyte large, right? So 4 kilobyte large. So the size of the size of the chunk, each chunk in a file is either different sized or smaller in size. So, but Google File System proposed that it's a fixed sized large chunk. And they also have the master chunk server clients architecture that we are going to look into today. So this is what Google File System proposed. And but why they propose this is very important, right? As I mentioned, the main key point of this class is not about what techniques, it's about why are they using these techniques in their design. So why they want large chunks? Because most of your files are large. If you have large chunks, the number of blocks that you need to maintain can be reduced. Plus, it also promotes the sequential locality in reading streams of data. And because your writes are also sequential, so large chunks is basically a very good idea. And as you learned before, if your basic chunks are large, your bandwidth could be more, could be better, right? So those are the reasons why they want large chunks. So a question that has been left since the last lecture is that why they propose the flat files flat structure. So my answer is this is actually for FIPS must support multiple concurrent operations. And the reason is because, well, if you are in a traditional conventional file system, if you are accessing a file, then it turns out that all the directory nodes within that's related to the file that you are accessing must be visited. And if your operations is trying to modify the directory content, the whole directory saying that if you are accessing homeway foo.c, the directory node called homeway will be locked by the process trying to modify foo.c, because when you are modifying foo.c, you can potentially relocate foo.c, which will change the content of the homeway directory. So it turns out that both the directory node and the file within that directory, which is the only file that you are accessing, both have to be locked. And because a process locked the directory node containing the file that you are accessing, no other processes can work on the directory that contains foo.c. So it turns out that your concurrent operations will be limited. However, if you have flat file system structure, means that when you are modifying foo.c, since the directory is simply an illusion, so you only need to lock the node of the entry of the file. You don't have to lock the whole directory. So that's how it supports multiple concurrent operations. And for the sixth, bandwidth is more critical than latency. I would say the flat file system structure has a side effect on both in a way that it actually improves both. So let me show you how that would happen. So that's why 6 is not the correct statement, because it's actually helping on both. So if you remember this story that we have been talking about, if you are trying to open a file in network file system, then it turns out that it will take at most 12 round trips to retrieve the directory node content, and real the metadata of the files and also the real content of the files. So it turns out you need this many round trips. But if you are using Google File System, since this is just a single entry, all you need is that, well, I send, I just look up for homeway food.c, and the Google File System will tell you, well, here are the locations containing homeway food.c, and the client just randomly chose one to access. And because the list is already telling you the data locations, so all you need to do is just send a request to the data location and retrieve the data directory. So originally you need 12, but now you only need 4. So in this way, when you are fetching the content of food.c, your latency is improved because you only need 4 round trips. And because within these 4 round trips, this round trip is used for retrieving data. So you can imagine your bandwidth also improved, because in the past, you can only use 1 out of 6 for your data traffic. But now you are actually using half of them for the effective data access. So your bandwidth also get improved. So that's a very significant improvement on both round trip delay and latency, the round trip latency and bandwidth. So it's a very, very neat design, very, very good idea using the flat structure, which I think is probably the best part of the Google File System, right? So that's how they achieve concurrent access. So the remaining thing that we haven't talked about, right? So we have talked about with large chunk size, we can solve this one, this one, this one, and this one. With flat structure, we can solve this one, right? So how they achieve the first goal, if you want to build a storage based on expensive disks that fail frequently. So the answer is that the master chunk server architecture. So how does that work? Before I show you the picture, I know you have read the paper, so why don't you try to use about 90 seconds to show me your understanding why GFS architecture can help. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, now let's go ahead and have a group discussion. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now let's invite one of the group to tell us your answer. Okay, Rogelio, what do you think?
Red team chose the answer is 3. 1, 2, and 3 are
Okay.
correct.
And why?
The fourth one doesn't make sense because the paper directly states that the client nor the chunk server's cache file data. And the first one is correct. If the one active server is referring to the master node in the cluster, then that is correct. The master stores and manipulates metadata about the file system. The second one is correct because the purpose of having multiple, well, one of the purposes is to have, of having multiple chunk servers is to have replicas among them, meaning that the data is replicated and we can balance the load between chunk servers. The third one is correct because the chunk servers are responsible for are controlling the data path, and then the master node is responsible for all control paths.
Okay. Other thoughts?
I might not be so okay. For the third one, the chunk server stores the data chunks and then replicates them. So I believe, yeah, 1, 2, and 3.
Okay, so so first of all, right, let's read the first one, right? So well, as most of you, right, the paper already said that well, the cluster only contains one masters, and some of you might be curious about, like, okay, what happened if the master fails? So what Google File System is talking about is that, well, so another thing, right? Another thing that you might also want to be noticed about is that, like the NFS, Google File System is also a file system that's promoting the idea of idempotent operations, meaning that, well, if the request failed, then because no one is caching the states for others, so you just retry. So the same idea has been used in Google File System in a way that, well, if the master failed, in the meantime, they will find a shadow master, and it will put up the service on the shadow master. However, the client may not find a master at a time, and if figure out that, well, there is a timeout, so my request cannot be accomplished. So what happened in the client is that it just requests the same, you just perform the same IO request again, right? So that's very similar to NFS. So that's why Google File System think, well, we don't need multiple masters, we only need one master, and we just put up the single master again, right? But they do have shadow masters to deal with the case that the active server failed. And the second thing, right? The chunk server in GFS may contain data that also can be found on other chunk server. So this is called replica. And the thing is that, well, by default, each piece of data in Google File System will be replicated for 3 times. So remember that whenever you put something on Google will copy your data, will create 3 copies of your data at least, right? So you think, well, so you think you delete something from Google server, but in the meantime, there might be 2 other replicas are also living somewhere else. Plus, the Google File System does the backup all the time. So you can imagine that, well, once you put something on Google File System, it's never gone, right? And because you have replica, they also have backup, right? So but the key thing is that because you have replica, so if any of the disk failed, you can find 2 other replicas to accommodate the case that the expensive disk failed all the time. And the third statement is actually incorrect. So the chunk server, well, again, as we said, the key point of data center is not to optimize for your performance, is not for your good, is for their good. So what the Google will do is not creating a server that's dedicated for your data storage. It's creating a server that can run as many services as possible. So in Google Data Center, in Google File System, your machine, the chunk server is simply one of the user level server process. And they can run a chunk server and a client. A client can be an application running MapReduce on Google Data Center as well on a chunk server, on the same server, as long as the machine resources are permitted. And so there's no strict there, like the sentence that I cite in the paper, right? It's easy to run both a chunk server and a client on the same machine as long as machine resource permit and lower reliability costs by running possibly flaky application code is acceptable, right? So the chunk server is not a dedicated server. And last thing, the client can cache file data to improve performance. A lot of you might think, well, that makes sense. However, the Google File System doesn't want the client or the chunk server to cache the file data, and there is another reason for that. We will talk about later. So it's unfortunately none of after discussion. Well, most of you get 1, 2. However, the third one, if you pay more attention, and again, think about the nature of data center, and that's one thing I do want to let you know is that, well, from a system architect's perspective, we will think that, well, we should have as many dedicated resources to a service as possible. However, it never happens in business. In fact, if you do that, that company will go bankrupt very soon. So, and I can tell you the story of Google's, when we talk about Google search, and that's how Yahoo failed and how Google success. And the key point is just the third one, because Google tried to save as much money as possible by promoting multi-tenancy. So a lot of you might consider Google is a company that put the customer as the first, but I just want to tell you, Google is still a company, and what Google is trying to optimize is definitely the amount of money they can earn from customers. So the third statement is not true, because if you think about that from the company's perspective, it's just a waste of money. So for Google File Systems architecture, the master chunk server is helping us to accommodate the case of expensive disk, because you can create 3 replicas by using inexpensive disks. And if one failed, you can find 2 other copies everywhere. So here is the big picture of the Google File System architecture. So if you have an application, the application still use the open, close, read, write file system call to tell the GFS client, which is a system level stop running on the client, the operating system's kernel space. And once it receives the file name and the size that the application wants to access, the GFS client will send that request to the master server, which is a single piece of machine, as we mentioned. And what's inside the master server is that it will translate the virtually hierarchical namespace into a tuple that contains the full directory, like the full bar, and the chunk index, meaning the offset within the file that you want to access, and use that as the input to a flat table, as we mentioned. And the table will give you the chunk location. And as we mentioned, right, each file have at least 3 locations. So the master will return all 3 locations to the GFS client. And the GFS client can choose which chunk location to access. So in this way, the GFS client chose the very left chunk server for the access. However, if the first one failed, it can definitely go to others. And if the first one does exist, the data that you are requesting, it just return the data directly to the application without going through the master again. So the key thing here is that, first of all, because you have multiple replicas within different chunk servers, so it helps us to achieve two goals. The first goal is load balancing, because your GFS client randomly chose one, and if your random seed is your random mechanism is good enough, you are supposed to achieve load balancing very well. And the other thing is that because you have replicas, if one failed, you can also get one from another, right? And the other thing is that a lot of people were worried about that. Well, the master server becomes a bottleneck. And at that time, Google's answer is this: because only the control path, the lookup of the file location, goes through the master, but the majority of the data traffic is directly go through the chunk server and the client. So the master is only performing this small lookup, so it's not heavy loaded. And that's another reason why the master chunk server architecture will work, because it actually decouples the data and control paths. So only the control traffic goes through the master. So that's the Google file system architecture. And another reason why they embrace the idea of single master server is because it vastly simplified their design and enable the master to make sophisticated chunk placement, because the master is the only one deciding the chunk allocation. So it makes all the mechanism becomes really simple, right? And it, as we mentioned, right, because the decoupled data and control path, so it minimizes the master server in reads and writes to avoid it become the bottleneck. So this is the distributed, another slide that used the text to describe the distributed architecture used by Google File System. The single master try to maintain the file system metadata, including the namespace, mapping access control, and chunk locations, and control system-wide activities, including garbage collection, and in case you want to migrate the chunks. And chunk server stores data chunks, and chunks are replicated to improve reliability. And again, 3 replicas are created. And the client uses APIs to interact with applications. And the clients directly interact with masters as well as chunk servers. And when it interact with master is only for control, and interact with chunk is only for accessing data. Again, chunk servers, they are not dedicated for data storage, because data storage is IO intensive operation. So your processor is underutilized. So they try to run as many clients as possible for the chunks to save money. And if you want to read data in Google File System, again, right, what happened is that the application request and the Google File System client will send the file name chunk index, and the master will return you the chunk handle, the chunk location, and you just pick one to access your data. And if you are writing, right, again, you create the request for the master, and master will tell you these are the place that I want you to write your data to. So you think it's the master will distribute the data for you, but actually the replica is also created by the client itself. So you are actually, so if you are running an application in Google File System, the client is responsible for sending its data 3 times to different servers. So the traffic is actually a lot between the client and the chunk server, and the chunk server themselves doesn't negotiate, it doesn't perform the data replication in general. So it's the client's responsibility to create those replicas. So that's the Google file system architecture. So, but sometimes, right, the primary server can also define the orders of updating chunk servers as well if when a write is created. However, the real data traffic is still going through the client and the chunk server directly, and the chunk server themselves just define the order of updates, but not dealing with the data traffic directly. So this is the writing data in Google File System. So an interesting thing to talk about, right? Consistency. So if you were in my computer architecture class, you probably know what a consistency is talk about. So the consistency here we are talking about is that since you have multiple copies, multiple replicas of data, how can you make sure that all of them are presenting the same content? Right? So that's the consistency we are caring about. However, Google File System is promoting a relaxed consistency model in a way that what it tried to do, right? So let's look at the consistency models that Google is trying to achieve. So if you have a write that write to a specific location, right? It actually have 3 different modes. So first one is that, well, if you have a write failure, right, it means that you have inconsistent data. So one of the client may have data that's different from others. And if you have a concurrent success state, means that your current data is consistent but undefined, means that, well, it only means that the chunk server, one of the chunk server have a value that's reflecting the change you made on the client. However, not all of them have the same content, right? So it's consistent between a client and a chunk server, but not with all chunk servers. Only the defined status tells you that all replicas has the same value and they reflect the new mutation and is consistent, right? And the other thing that if you are having a pen-only traffic, the data, they can only guarantee that it's defined, meaning that replicas reflect the mutation. However, it may be inconsistent among chunk servers. So as you can see, right, Google File System doesn't always guarantee that all your replicas are giving you the same up-to-date data, right? So like the consistent, it only tells you that all replica has the same value, but it doesn't mean that the value reflects your up-to-date data, right? And only even for the defined, it could be inconsistent among different clients. So who will deal with that? So Google File System doesn't deal with that. And it says that it's the application's responsibility to deal with that. So being a programmer, if you are dealing with a distributed file system like Google File System, a lot of you might be very naive about thinking that, well, the Google File System will deal with the file content correctly for me. The answer is that no, Google is not that kind of company. It says that if you are a good programmer, you should deal with that yourself. So that's the Google File System, that the Google File System doesn't always reflect the latest content of your client. And even though some of the chunk server reflects that, not all the replicas reflects that, right? So that's the Google File System. So a lot of things application designer has to deal with that. And what kind of application model, what kind of programming model Google File System propose on their data center is actually MapReduce when the time the paper is published. So some of you saying about like, well, MapReduce, that's an old model, but it's actually the standard of programming model that we are still in use. So some of you saying that we are using Spark now, but if you check the detail of the Spark, it still have the same semantics as MapReduce. The only thing that is different is that Spark trying to cache as much data as possible in your main memory. That's the main difference, because they have the RDD abstraction. But other than that, it still use the MapReduce syntax, the same idea of MapReduce. So this question, I don't want to ask you to answer, because we actually didn't assign the MapReduce paper to you. But if you check the nature of MapReduce paper, right? The MapReduce its library in user program splits the input file into 64 megabyte. Doesn't that sound familiar, right? Remember, what's the chunk size we have in Google file system? Is actually 64 megabytes. So because your Google file system is designed in such a way, so the MapReduce is and why the Google file system is designed in such a way, because MapReduce typically wants the input file to be in this size, right? So that's why 64 megabytes makes sense. And between 16 to 64 megabytes, they chose the 64 because, as we mentioned, this would optimize for the bandwidth. And why bandwidth is important? Because the input data is usually large and across hundreds of thousand machines in order to finish it in a reasonable amount of time, right? Again, the wording reasonable amount of time is very interesting. What does that mean? A lot of you think about, well, use MapReduce, my program can finish faster. The answer is probably no, because if you read a sentence, right, what MapReduce trying to accomplish, that we just want your job to finish in a reasonable amount of time, not the shortest amount of time, because MapReduce actually aims at computation throughput rather than the latency. So if you look at this question, actually everything it tells you the characteristic of MapReduce in a way that MapReduce is a massive parallel programming model where you decompose your program task into a lot of workers. You can consider a worker as a process which read chunks of your input file and compute on this chunk of input file. And why am I saying this is a process? Because each of the worker, they works independently and do not share data. So they are process-based rather than thread-based. And each work does not override its input in general. So you can imagine MapReduce is a really intensive and append only in write, because it never overrides its input. If you want to create some outputs, it's append only because it never overrides its input. And it's aiming at throughputs like bandwidth instead of latency, right? So if this is the main programming model that runs on top of Google file system, that makes a lot of sense now, right? So, but let's give an overview of the MapReduce model. So first of all, in a user application, you will fork a master process as the control process, and you have a few workers that your user application will create. And we use fork here because, as we mentioned, since each of the worker they work independently, so each worker is essentially a process. And the master process is the control process. It assigns the map function, which reads your input, and the reduce function, which reads the output from the map function. So what would happen is that you put your inputs into different chunks, and your workers will grab those inputs from different chunks. And after processing input chunks, you will get a few outputs. And this intermediate output, the workers can interleave those intermediate outputs, and use them as the input for the next stage. So this is called MapReduce. And the reason why it's called MapReduce, because you have the map function, which treat your inputs individually and generate the individual outputs. And the individual outputs, intermediate outputs, could be, and the workers can take multiple individual intermediate outputs as its input and generate a final result to different output files. So this is the whole MapReduce model. And as we mentioned, the input never gets overwrite, and the output file, because it's also independent pieces in each worker, so they are append only traffic. So, and there's no sharing among workers, and they never overwrite the input. So if you look at, this is the application behavior on Google File System, then the design of Google File System actually makes a lot of sense, right? Because MapReduce is fault tolerant. If one of the worker failed, we just retry the worker, and because your master would know, wow, one of the workers did not finish its job, so we just restart the worker, reassign its input to somebody else, right? So it's very fault tolerant, and MapReduce aims at processing larger amount of data once, and as you can tell, right, each file chunk is at least like 60 megabyte large. So it's having large files as its input, comparing with the small files for personal data. And MapReduce, as we can see, right, reads chunks of large files, so primarily reading streams of data. And the output is writes, because you just keep growing your output as your workers keep writing to its own log, and it never overrides its input. And you must support multiple concurrent operations, because your MapReduce model has thousands of workers simultaneously. And bandwidth is more critical than latency, because as we saw in the paper, MapReduce only wants to finish tasks within a reasonable amount of time, not the shortest latency. So, and if you look at all these three things, right, you will find out why they designed Google File System, because this is what they want for MapReduce, right? So that's why Google File System looks like that. But actually, Google File System is a very interesting paper. So if you read section 7, it actually tells you that, well, we also, when we developed the the Google File System, we actually found there are a few Linux problems. So Google is a very intensive user of Ubuntu, or say in general Debian Linux. So so that's why when we are doing this project, I use Ubuntu system, and as you can tell, because even for Google themselves, they are using the Ubuntu files, Linux operating system in their company, right? So and they try to contribute their stuff into the Ubuntu system as well. And they actually found the Ubuntu system, or say in general the Linux kernel at that time, they have quite a few issues. For first of all, the driver, the disk do not report their capabilities honestly. So a lot of you might have the question, like sometimes once a day you found some people telling you, hey, here's a tool, it can tell you how healthy your hard disk or solid state drive is. And then there are always some sensor failure. And sometimes it's indeed the sensor failure, sometimes it's the hard disk failure, and sometimes just because some of the vendors, they do not report their capabilities honestly. So if you are trying to optimize your system based on those, that's not convincing, right? And the other thing is that well, so in default, right? When you are performing file operations, because we want to minimize the latency, so we try to cache as many stuff as possible. So it turns out that there are cases that your disk data is inconsistent with your cached data. So to force your cached data to be written back to your disk, there is a file system called fsync that should help you to write back your data to your chunk. However, they found the cost of fsync is actually in proportion to the file size rather than your updated chunk size, right? And that's not too hard to imagine, because if you think about the log structure file system, as we mentioned, right, we want to keep the whole chunk updated. So when we perform fsync, it turns out that we are going to relocate the whole file to some other places. So it turns out that it's proportional to file size, because you are actually trying to sync the whole file rather than just the updated chunk. And however, in Google File System, as they are doing the append only, right? And they are having very, very large files. And if you have append only traffic, right, the only thing that you need is to change, or say is to change the parts that you updated, right? Then then you should not have your fsync call to be proportional to the file size, because a large portion of the file which you are reading only should not be updated. And the other thing is that, well, mmap, you are very, very familiar with mmap now, right? So there is also an issue of mmap in a way that, well, mmap is a glibc call. Once you call it, it will invoke the glibc and the system library to allocate a virtual address for you. And it's up to your kernel module to decide what physical address you want to map to that virtual address. However, the mmap has an issue in a way that it has an implicit reader-write lock that only one process at a time can call mmap. Other processes have to hang on there, even though they are requesting different virtual memory addresses. So that actually causes a traffic on a bottleneck on concurrent access. And they claim it's a good thing because the open source nature of the Linux, they can fix it and contribute to the rest of the community, right? So, however, Google take advantage from the open source community a lot. What they do? So they say, well, for our Google file system, when appropriate, we will improve the kernel and share the changes to the open source community, but it's never open source. So sometimes don't trust Google too much, right? Even though they say, well, thanks the open source community, we can fix it and we can contribute, but when appropriate, right? You never know when is the time. And another thing, right? Google tried to try to convince us that single master design is good because it makes things simple, and it claims it's not going to be bottleneck. And it tried to use in-memory data structure to make the lookup as fast as possible, right? But what if the master server fails, right? And the thing is that they have shadow master, right? So that's what they try to say. However, in a paper they published in 2012, they say they have a new file system called Colossus. It's the successor of Google file system. Well, unfortunately, Google never talked about the design of their new Google file system. However, from a paper that's published in ACMQ, it has a case study, evolution on fast forward. And what they say in a Q&A actually revealed to you some of the modification about that, right? So, okay, so one thing, right? So the interesting here is that in this part, they mentioned that, well, we have a single, well, so first of all, right, in their new file system, right, they use a multi-cell approach, basically made it possible to put multi-GFS masters on top of a pool of chunk servers. So this one, it tells you that, well, although the Google file system tried to convince you that you should only need a single master, however, later on, they are trying to, they actually build a new file system with multiple GFS masters. And the other thing, right, another sentence that you can find evidence that they finally abandoned the single master design is that they prove that the single master becomes a bottleneck for clients, even though the clients issues few metadata operations themselves, right? So turns out that, well, the paper initially talked to you about like the Google file system. If you want to build a file system like Google file system, you only need a single master. But turns out that when time goes by, when Google grows up, the traffic changes, the application changes. So single master is no longer a good design. So don't take it too seriously, right? So another thing, right? They say they want large chunk size only. However, we said that in 2003, the Google file system is only supporting services like Google Search, MapReduce, or Bigtable. Those are big files. But now, the most frequent used service that you might interact with Google every day, probably no longer Google Search, but Gmail, right? Like even UCR, we put our mail servers on Gmail. So, and a lot of emails, they are terribly small, right? So turns out that because they have the Gmail service, so they need to support small file chunk size, right? So, so they actually provide so they said, right, they have to accommodate the case that you have an average of 1 mega file size, which is probably the size of your email chains as well, right? So that's another evolution of GFS. So GFS, as we see, is also a moving target. Right. So another thing that I do want you to keep in mind as you are reading papers about the system design, always think about, well, why they come up with that design at that time, right? So that's why I don't talk about those what in very deep, but I do want you to think about what kind of problem the what solves. Because if you look at what Google File System want to accommodate now, a lot of what they proposed in the past doesn't make sense anymore because the workload changed, right? Because now they have to support Gmail. So the large chunk size is no longer a good idea. Because the company grows, the number of clients also grows. So single master server is no longer a good idea, right? So those are things that you have to keep in mind. You have to keep in mind, right? Time changes. And this paper is also very interesting. And there are a lot of stuff that we don't have a chance to talk about, but they are really interesting, like snapshots, namespace locking, replica placement, create replication, rebalancing, object collection, stable replica detection, data integrity, diagnostic tools. So those are lots of other interesting things that you can learn from this paper. So I do encourage you to read this paper in depth. And finally, let's have have a review of what they achieved, right? So first of all, for inexpensive disks that failed frequently, they use replication and they create 3 replicas for each pieces of data. And it's a distributed storage architecture. So if one machine failed, you can find another machine. And another thing is that many large files in contrast to small files for personal data. So that's why they have the large chunk file size. And but now, as you can see in a paper, right, it's no more possible because the Gmail service actually have the small file dominated traffic. And primary reading streams of data, that's probably still true. And sequential writes append to the end of existing files and must support. And those are achieved by large chunk size. And support multiple concurrent operations, that's by the flag structure, and bandwidth is more critical than latency. That's also by large chunk size. And flag structure also can help bandwidth and both the latency. So that's why I don't put it in the last one, because it actually helps on both. And I think that's probably the most neat idea in Google File System. So what's missing in Google File System? So think about that, right? The consistency models that they support is relaxed consistency. So it puts a lot of pressures on the programmer to maintain the data consistency. And because it has the single master, so the scalability is actually a big issue when your service scale up. And it's only efficient in dealing with large data. So that's why they have to support, modify their file system to support service like Gmail. And another thing is that they don't consider the geo redundancy in a way in a very early design, because Google were a small company at the very beginning. So the original Google File System design doesn't consider the case that they should replicate the Google File System to a lot of different places. And why this is important, right? So let me tell you a story. Like there are well, when I was a student in UC San Diego, right? There were a night that that's probably the night that I spent most time with my roommate, because we were in a blackout for the whole night. I remember it starts from 6 o'clock, and the electricity is not back until the end of the day. And well, because it's still early and we cannot do anything, so I still remember the night that both of us, we sit on the couch, we share a lot of peace of mind at that moment. And well, that's actually a very blessing moment of time, but it would be a more blessing moment of time if I have the electricity that I can use to watch the YouTube or work on my job, right? So but that's actually reminds me that, well, even though we are in the 21st century, the electricity is really fragile. And the interesting story is that there were a huge strong wind blowing down one of the tree in Arizona. And if you are familiar with where San Diego is actually on the most southwest corner of the United States. And as a result, it only have two sides connecting to the west side of the United States. One way is going to Arizona, the other way is going to the Orange County, like Irvine. So it turns out what happened is that because the tree were down, and the tower supplying the electricity caused there is a high voltage going up to the north of San Diego. So the other part also get the other part of the circuits that's supplying the electricity to San Diego also gets burned. So both sides does not provide electricity to San Diego. So that's why the San Diego is out of electricity for a total of 6 hours. And it turns out that it takes them the whole night to figure out, well, where in the desert the tower is down, and trying to fix that, right? So that was my experience. And another thing which is related to the song that we played before the lecture is that, well, the song we played today is Perfect by Ed Sheeran and Beyonce, right? So Beyonce, as you know, she is a very, very great singer, and because she is so great, so she was also invited to the Super Bowl halftime show in 2013 after Katy Perry, as far as I believe. And turns out that after her show, right, the Super Bowl stadium get black out because Beyonce is too hot. No, that's not a reason. But some people were suggesting that because the electricity used by Beyonce's performance is too much. So it turns out it's overloaded, and the broadcast was interrupted for 34 minutes. Right. So even for Super Bowl, such an important event, you still cannot prevent the power outage. And needless to say, right. So some people would say, well, so would suggest that, well, is Beyonce caused the Super Bowl blackout? Maybe, right? It's still an unknown, right? And if you live in California, you probably remember that the PG&E, a notorious company in the northern part of the California that supplies the electricity of the Silicon Valley, but unfortunately, the poor managed company, they because they caused the wildfire for their outdated electricity network, so they cut the power every time when the temperature goes up and there's a potential of fires, right? So a lot of people feel like, well, California is a bad place, so they migrate to Texas. But unfortunately, Texas, so from some of you also learned recently, because they rarely have snow, so the snow caused the power outage issue as well, right? So you can see that even in 21st century, even though you are living in United States of America, blackout is still an issue. So if you want to keep your service still available all the time, you really should read how Microsoft does their file system. So if you think about, so what's different between the Windows Azure storage? So Windows Azure is actually 10 years later than the Google file system. And you know, like Microsoft is never the innovator, and it's usually the catch up, the company tried to catch up. However, because the company, they hold a lot of business customers, so they still have the momentum to grow up, and they can always learn from the mistake that other people made. So there are so Microsoft is very different from Google in a way that Google doesn't have a lot of enterprise level clients at the time that Google was growing. In contrast, Microsoft has that, and because of that, right? So Microsoft actually have a pretty different breakdown of their data that people want to store, and very different requirement that for the data storage. And the other thing is that Microsoft also have a different kind of service which you might use every day called Xbox. Also demonstrate very different behavior as Google service, right? And some of you might never heard about this, but this is actually you can think it's a Microsoft Music, right? So like a Apple Music service. So if you look at the this traffic, you can find that a lot of this, right? They have different breakdown of the traffic, and it turns out that like database tables still accounts for about half of the traffic. However, the blob means the large binary files is only account for 18% of their requests. On the other hand, what they call Q is small messages are accounting for 35% of Microsoft's traffic. And why is that, right? So if you look at the service complex of Windows Azure storage, they need to provide a cloud service platform for social network. For example, remember, Skype is part of the Microsoft, right? And it used to be like Microsoft also have Messenger or this kind of service, right? But Skype is one of the service that represent Microsoft social network application with small message, right? And video streaming, in the past, Microsoft also have their real-time video streaming service, Xbox gaming, records management for those companies, and also Office, right? And Astra in Microsoft, right? So it turns out that in contrast to the big table map reduce that Google search that Google has to deal with, Windows has, or Microsoft has to deal with a lot of different applications. So they have different data abstractions. So they have binary large objects called blobs, like pictures, Excel files, HTML, hard disk images, or logs, database backup, pretty much everything. And database tables, because a lot of people use Microsoft data centers, and messages, right? For example, your Skype message, your Xbox messages, right? So those are the stuff that Microsoft has to deal with for their customers. So within these three different data types, we can imagine blobs are large, tables are large. However, the messages, they are small. So unlike Google File System, everything is large. Windows Azure actually have a significant amount of small things they have to deal with. Another thing is that, as I mentioned, right, Google File System is only deal with their own service and end users, and they know end users won't complain too much about them, because the strategy of Google File System, or say Google service, is that they don't charge you, right? Since you are not paying anything, we don't care, right? Your inconvenience, and you should know that your inconvenience is because you don't pay, right? However, Microsoft is a different company. They charge you for everything. However, because you are charged, so we want to guarantee you have the best service. So instead of the relaxed consistency, Microsoft want to support strong consistency. And the other thing is that they also learned that, well, Google File System as a single master is not scalable. So they want to have a scalable namespace storage. The other thing, as we mentioned, Microsoft they know their customers are everywhere. They don't want any minute their service to be interrupted. So they want to have a service that, even though there's an earthquake, even though there is a wildfire, even though there is a snow, the service is still going on. So even though you have a disaster, we want to recover as soon as possible. And finally, again, for the company, right? We still care about the cost. We still care if we can make a single server being utilized as much as possible. So how they solve the issue? and surprisingly simple. All problems in computer science can be solved by adding another level of indirection. So this is what Windows Azure proposed. As you can see, they have the storage stamp, and they have a lot of different layers. So 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 today we are going to talk. So how are we going to talk? So we are going to talk about each of this component uh, in in very detail. So so this is so but before we start talking about each small component, let's start by the high level concept of Windows Azure storage. So as we mentioned, the whole idea of Windows Azure storage is adding another layer. So what's the layer they add on top of the original Google file system, right? So you can imagine each storage stamp is essentially like a Google file system, right? So this one is like a Google file system, and each stamp is a 10 to 20 racks with 18 disk heavy storage nodes. So each of the disk heavy storage nodes, you can consider it as a chunk server. And so this is the stamp. You can consider this hosting as a Google file system. But on top of this, they have all sorts of other things, right? Sorry, this stamp, right? So so how they use this other things? So first of all, an application requests the file. However, instead of maintaining the same abstraction, the same file system abstraction as Google file system, this is what Windows do. It propose an URI, the Unified Resource Identifier. So like a web address, which is composed of HTTPS / account name, your account with Windows Azure storage, what kind of service that you are using, .core.windows.net / partition name and object name. So look at this, right? They finally abandoned the hierarchical namespace. They just tell you that partition the object name you want, and then sending this to the client, and the client will issue this request to DNS, right? Because this is like an URL you use in a webs in World Wide Web. So this part of the address can go to the DNS service, which would dynamically translate your domain name to an IP address. And when they translate this IP address, they have to look up if this account name is available to access a set of locations. And then it will return the virtual IP of stamps that the client can access, right? And the client can use the return virtual IP to access the dedicated stamp for the partition and the object name at the end, right? So as you can see, the domain name service helps the Windows Azure system to maintain the load balancing. So this is somehow a little bit similar to another layer of the master server of Google file system. However, unlike the Google file system directly tell you where your data is, it only tells you which machine you can ask for your data. And so, and DNS, as you know, right? DNS, you can have multiple DNS servers. So there is not really a single DNS server. So this is automatically replicated. This is automatically load balanced, and because it randomly give you a virtual IP, so it helps to maintain the load balancing among different stamps. And because the DNS only tells you where is the stamp server, so it doesn't need to maintain the consistency of the data itself. It only tells you, well, you can find your data there. And it's up to the server to, or other layers to maintain the consistency of their data. So that's the layer they propose, right? And now, and the thing is that, right, because you have the DNS server, you can actually return the IP address to any servers anywhere on Earth. So it also helps the Microsoft service to be easily replicated across the anywhere on the earth, right? So that's how they also help the to maintain a file system in multiple geographic locations. So we said that STAMP is very similar to Google file system. So let's see how similar it is. So as we mentioned, right, the Google file system has master master chunk server, right? So similarly, in a STAMP, they also have the string manager and the extend node. So now I want to ask you, right? The string is used a lot in Windows Azure storage. Can you identify what's the meaning of string in Windows Azure storage? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now looks like we definitely need some kind of discussion. So go ahead and start. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, I do believe different teams have different answers. So can I have one of you share your thoughts? Okay, Andrew, what do you think?
Our team think all four are correct.
Okay, so can you explain a little bit?
So for the first one, actually all four answer can be found in the paper in section 4. I think it all have a direct sentence regarding to each answer. So for the first one, the stream is a list of extents. I think it's being explained in the either the
So you said basically everything can be found in which part of the paper?
section 4. Yeah, section 4.
Section 4. Right. So, okay, because we are running out of time, so we are probably going to explain that in the next lecture. But you are right. Everything can. I actually trying to copy the sentence from there to make sure that if you really find the answers in the section 4, right? So we are going to start talk. And thanks for Andrew. And I think you guys got the right answer. So we are going to start the discussion on what a stream is. Starting from the in the beginning of the next lecture. Before you leave the classroom, a few things that I want to let you know. I know a lot of you are probably feeling a little bit tired about the project, but let me tell you about this, right? So no matter what you have submitted tonight, and I will try my best to give you the first round of grading. And why I'm saying this is the first round of grading, because after I give you the first round of grading, I will tell you what are the cases that you failed. And you have another week to fix the cases that you failed. And to encourage you to fix those cases, you could you can still get 80% of the remaining grades that you missed in the first round. So saying that, well, if you only get 60% of the grades in the first round, if you fix everything before 11th, you can still get 60% plus 80% times the remaining 40%, which is the 92% of the total grades. Sounds like a good deal, right? You don't lose a lot, right? So and so hopefully that would give you some release if you still have some features that you don't think is working, because I don't think the penalty is really that much. And the other thing is that there is an IEval going on. And I do want to encourage you to express your thoughts about this class. The good thing about this class, if you have any, and if you think there are things that other courses, other professors, or the whole university should adopt, definitely let them know. And also another thing which I do want to apologize, because we have insufficient understaffed situation. So sometimes I can't, and sometimes like I have to sleep, so I cannot like respond to your email or Piazza post in a very short period of time. But that's also because we are kind of understaffed, and I'm the only staff, right? And finally, I care about the final exam. So the final exam, it will contain 2 parts, which is my the first time I tried this. So part 1 will consist of an unlimited time portion, which you will have open-ended question that you can spend about 6 days to think about the answer. And there will also be traditional multiple choice, multiple answer questions. When I say multiple answers question, it means that instead of a single answer from a question, this time you are going to have questions that might have multiple answers. And the other thing which I don't want you to do, because I know a lot of you would like to put as much answers as possible. So if you try to put everything in the answer, you will lose all your points, because we are going to give you penalties if you select an incorrect answer. So be careful about your selection. And in addition to those multiple choice, multiple answers question, you are going to see two problem sets that's representing the comprehensive exam questions. So this is an overview of the final exam, and I will reveal more detail in the next week. However, that's probably everything I want to tell you about today. And enjoy your night, and hopefully you can sing the song perfect to your project. Rogelio, do you have a question?
Yes. If a master's student is not doing the comprehensive exam route, do they still have to answer the comprehensive questions?
What do you mean?
So because students who are, for example, I'm in the BSMS program, and I had the option to take the comprehensive exam route, but I instead chose to do a project instead for my master's. Meaning,
well, I mean, the comprehensive exam question, everyone has to answer. It's part of your grades. But those are, okay, so let me explain that, right? The comprehensive exam question, everyone has to answer. And for those of you who chose the comprehensive exam as your grading graduate criteria, those two questions are especially important for you, because if you don't pass on these two questions, you cannot graduate.
Thank you.
Make sense? All right. Okay, other than that, enjoy the rest of your night. I will see you on Thursday.
I found a love for me. Well, darling, just dive right in and follow my lead. Well, I found a girl, beautiful and sweet.